Yeah, welcome to Strong Field Physics. Today we will first conclude our chapter on interference effects, and then I will give an overview of molecular physics with intense laser fields. So last week we discussed how to bring together our classical model with the photon picture, where we have immediately the appearance of ATI peaks, which we did not observe so far in the classical model. So we turned our classical model into a semi-classical model by introducing the classical action as a means to associate our electron trajectories with a phase. And using that phase, we can then calculate the coherent sum of all interfering trajectories. Interfering trajectories are, of course, those that end up at the final state, at the same final state, which means the same final momentum on the detector. We used this classical action then to calculate the phases of two trajectories that are launched as separated by exactly one optical cycle. And we found that by assuming that those are representing interference maxima of ATI peaks, we could find the formula for the peak position of the ATI peaks that we derived from the photon picture, where we took into account the ponderomotive shift of the ATI peaks. Yeah, and can you please show the presentation? Oops, I did not. There we are. Yeah. So this is basically how far we got last time. So until page 105. Until the end of the ATI peaks for direct electrons. Today we will take a look at a second type of interference and the so-called photoelectron holography. Okay, so our idea how to find the interfering trajectories worked like this. We plot here the electric field and, more importantly, the vector potential. Yeah, this here, the vector potential. And then we look for all points where the vector potential is equal. And then we know that according to the strong field approximation, trajectories initialized at these points here, so these circles and these triangles, they end up at the same final state, so they can interfere. By analyzing ATI peaks, we looked at only circles or only triangles. And now we will actually look at interference between the circles and the triangles. And these two times are in the same laser field. In the same laser cycle. Yeah? And they are here within even the same half cycle. But one is born at one point, the electron trajectory is born at a negative field strength, and the other time at a positive field strength. And the consequence of that is that one of the trajectories will interfere. One of the trajectories will recollide, whereas the other one does not recollide, and it's a direct trajectory. Okay, let's switch to the iPad. Oh, I forgot to scroll down on this one here. And displace my, okay. So we're almost there. Yeah, okay. So this, by the way, this was the final result of last week's calculation, and now we begin with 7.3 intra-cycle or ballistic interferences. Okay, so we found that in each laser cycles there is a pair. Yeah, there are two trajectories that are represented by the same vector potential, but different electric field strength. Yeah, so in each cycle, or actually we could even say each half cycle, there is a pair of initial times. Yeah, so we call them T naught 1 and T naught 2 with A of T naught 1 equals A of T naught 2, but E of T01 equals minus E of T02. And the consequence is that these two trajectories will interfere, but one recollides, the other one doesn't. These trajectories interfere, but one is a direct, the other one a recolliding trajectory. We will assume now that the recolliding trajectories recollides but doesn't scatter. Yeah, so if we assume scattering, then the the canonical momentum, so the conservation of canonical momentum, is actually violated, as we saw in the most extreme case, in the case of backscattering. Yeah, and then there we calculated, or we used the canonical momentum to relate the recollision momentum to the initial time, and then we inverted the velocity vector, and after this inversion we used again the canonical momentum to relate the final drift momentum to the recollision momentum. Yeah. So here we will assume that no scattering takes place, at least no scattering takes place. The more general case in which scattering takes place is the next section on photoelectron holography, which we will go through a little briefly to allow more time for the molecules afterwards. We assume that that scattering does not take place upon recollision. Otherwise, the initial times are not, or the initial vector potentials are not exactly the same, because one has this change in vector potential, or the change of canonical momentum upon recollision. The above conditions are not fulfilled. Okay, what we'll do now is we'll make a sketch of the electric field and the vector potential. as a function of time. Yes, so we have here our, yes, let's say this is the vector potential, A of t, and this is the electric field. So it must have the zero crossings here. Okay, so we have two initial times, yes, with the same vector potential. So it's this time and that time, to stick to the previous notation. Actually, I think this one was the circle, right? Yes. This one was the circle, this one was the triangle, okay. Yeah, so we have, but the important part is this one and this one. Now, let's see what happens now if we change the value of the vector potential here. This value, let's call this A of t naught, t naught 1 or t naught 2. And let's say we, maybe we can make a first statement about these two times here. These two times, t01 and t02. Yeah, quite obviously, that's the 2 here. Yeah, so t02 minus t01. This time difference is quite obviously smaller than t. Actually, usually even smaller than t, or actually, yes, it's always smaller than t over 2 even. But the point is that we can estimate the separation of the interference maxima and minima from this condition. Yeah, so for ATI, we had one optical cycle time difference, which led to an energy difference of h bar omega, yeah, so 1 photon energy. Here, the time difference is smaller. Therefore, the modulation period must be larger. Yeah, so the modulation period is larger than h bar omega. Yeah, so this means it's a sort of a superstructure on top of the ATI peaks. Then the next, so this is one thing, and another thing that we can derive is now if we change the value, for example, to lower vector potentials, yeah, so the line would be then somewhere here, then this time then the time difference increases, right? This one moves here, this one moves there. If we go to smaller values, then the time difference gets shorter. This means we can conclude that now the time difference is no longer constant, but as we go to higher energy or higher vector potentials, we end up at a smaller time difference and therefore a larger period of the modulations. Yeah, delta t decreases as we move towards modulus A equals the maximum of A. Or we could also say as A increases. Yeah, and so the energy spacing increases with increasing drift energy. And quite trivially, yeah, so if we go to the cutoff to the maximum energy, 2UP, then the time difference is 0, and there is an interference maximum. There is Let's say it's trivial. A trivial interference maximum at 2up, since, well, delta t equals, maybe TO1 equals TO2. And so the vector potential is at its maximum. Now, if you want to do this numerically, a good way is to basically do exactly what we showed here initially. Can you show the presentation? Yeah. So you draw a line here for the vector potential that you're interested in, or for the energy value that you're interested in, and you identify all these times. And then, as we did for the ATI peaks, you calculate the final momentum and the final phase, and then you calculate the coherent sum of all these trajectories. Yeah. Okay. So, yes, please. A smaller modulation time in order to observe these interference effects. I'm not sure I understand the question. Yeah, you. So they have a larger separation than the ATI peaks in momentum. So in the final electron spectra. And so what this looks like on. Can you also show your iPad? So what this looks like is so first of all, at 2up, we have a trivial. We have an interference maximum, and then we have at some point a minimum, and then the modulation, the spacing, increases with increasing energy, right? So they go here towards increasing energy. So now we need to make them a bit shorter. Yeah, this would be if we only had those, this is now not weighted by the ionization yield, yeah? Of course, you would have a lot more counts here, but it's easier to draw it this way. And this actually, and the ATI peaks, they have this fixed period, so they lie underneath. So I'll try to draw this in gray. Yeah, so this looks like this then. And basically you can observe them as modulation of the peak height of the ATI peaks. And again, what I'm neglecting here is this overlying slope that would look something like this. Yeah. And so these here would be the ATI peaks. And this here would be the superstructure on top of the ATI peaks. In the seminar, I will show a result of a numerical calculation of both the ATI peaks and the these ballistic interferences. Yeah, this is it looks quite like what I drew here. What I can show you here is the result of an experiment together with numerical calculations. So this experiment is actually similar to the one that I showed you a couple of weeks ago, where we observed the ponderomotive shift of the ATI peaks. This is also what can be seen here. Yeah, this is classical or semi-classical calculations where only the ATI peaks are taken into account. However, instead of looking at the yield of the photoelectrons, we actually look here at the asymmetry of the left and the right spectra. Yeah, so I don't want to go into all the details here, but here you basically see the ATI peaks with this typical decrease of the peak position with increasing intensity. And here, on top of these peaks here, we have here these ballistic interferences. And you see that the spacing actually becomes closer as you go to lower energy. Yeah, so at here, this is close to, this is actually 1 UP, so it goes up to 2 UP there. This is not shown. Yeah, so at 2 UP, there's a trivial maximum, and here, even at 1 UP, there's this strong maximum. At this position, this has some, like the intensity dependence is maybe more surprising or different than one would trivially expect. Yeah? In any case, these modulations that were calculated here were also seen in this experiment, and in the however, in the photoelectron yield, you don't actually see these modulations. You only see them when you look at the CP dependence of the photoionization. Okay, let's go back to the iPad. Yes, please. Yes, these are low energies. Yeah, these are the direct electrons. Yes.
You go back to the
of course. Yeah.
Like we have the wave
So what was done here? So this was measured with an 800 nanometer few cycle pulse, and with a CP stable pulse. And then we were looking at the asymmetry, and the special thing here is that the energy is actually scaled in units of the ponderomotive potential. Yeah, and so what's one here, for example, 1 UP here corresponds to much lower energies at the low intensity than at the high intensities. Yeah, so if you plot this in the conventional way with electron volts, then these almost horizontal lines, they would actually go straight up. And this shows basically that the position of the interference maxima due to these ballistic interferences, they are almost constant in terms of the ponderomotive potential. And this is actually this makes a lot of sense, because we saw in our previous calculation 7.8. Maybe you can show the iPad. Yeah. So we had here the So yeah, so in the script this is equation 7.8, but I didn't label them, so I have to find which one it is. We found, in any case, we found that the action of a trajectory scales with the ponderomotive potential. And what's the best equation to see this? Yeah, I guess this one here, yeah? So if you ignore the constant offset, then you can put UP in front of it, and you will see that the action scales with UP times T. And the action of a single trajectory. And therefore, as you go to longer wavelengths or higher intensities, you will get more modulations, but the position is almost independent because it scales with UP.
So after UP, what will happen to the modulations?
After UP, after 2 UP. Yeah, after 2 UP, we have to look at rescattering, because only then we can reach these energies. Well, in the limit where of the strong field approximation. Yeah, so in reality, one also obtains direct electrons with slightly higher energy. Okay, yeah, let's move on to holography. So the idea here is previously we discussed these interferences in one dimension. Yeah? So we looked at time differences and related these to energy differences. But if we move to, we can add here a spatial dimension, yeah? And then we have to look in momentum space, because the conjugate variable to position is momentum. And the appearing interferences there are then called holographic interferences, which was proposed in a paper in 2011, which made a large impact. I think I forgot to put that on my slides, though. Yes, please.
On the second iPad for the scientific.
Yeah,
But I didn't. Thanks.
this one?
Yeah. Thank you.
Ah, yeah, okay. Okay, so a short overview of what this is. Photoelectron holography. So previously we discussed delta T, and this led to some delta E. Now add a spatial dimension. And then we have to look at difference in momenta. Okay. So let's consider the case where, we have here our atom that provides the electron, and then the electron is driven out and recollides. And now we consider the recolliding electron as a wave, a wave that, here scatters on this ion. And then we can divide our wave here in a part that remains unscattered. Yeah, so it basically just propagates straight forward, approximately as a plane wave. So of course that's not really a plane wave, because the ion here clearly has is an ion and therefore has a Coulomb potential, and that leads to a curvature of the wavefronts. But we'll neglect that, and then we can divide this again into the unscattered plane wave and a scattered spherical wave. Yeah, so in a way we're applying here the Huygens principle, because the wave that's scattered is here emitted from this atom, and therefore it's a spherical wave. Okay, now can you show in addition the presentation? Okay, so the situation that we have is we have this spherical wave here, and we have a plane wave, and now they interfere. Yeah, so I add up the real and the imaginary parts of these of the waves, and shown here is the real part of the wave function. So this shows these rings, and in addition it has here some structure. And however, what we measure, of course, is the square of the wave function. And so when I show this, we get this interesting type of distribution, yeah, where we have here interference maxima and minima that spread out like this. Okay, and now with this picture in mind, let's take a look at momentum distributions. Yeah, so I am motivated that now, since we consider scattering well, well, at least two spatial dimensions, we have to look in momentum space, and this is what's shown here. So this is so-called velocity map imaging result. Yeah, so this shows the momentum distribution of the photoelectrons along the polarization in this axis and here perpendicular to it. And you notice these interesting stripes here. Yeah, and these are quite reminiscent of these stripes that we observe, that we predicted here from our scattering picture. Yeah? And the idea now is that when you have a wave that is more or less well known, namely the the plane wave, and then interferes with an unknown wave that carries information. Yeah, the scattered wave carries information of from the scattering object, and you record the interference of the two. Then you can, in principle, reconstruct the shape of the scattering object. This is a well-known technique named holography. Yeah, maybe you can show this in large. So this is an optical technique. So this is conventional holography, optical holography. Holography, you use a coherent light beam, send it through a beam splitter, and then have one part of the beam illuminating an object, and the other part does not illuminate the object, and the interference of the unscattered and the scattered waves are recorded on a photographic plate. And then, if later on you illuminate the photographic plate with the reference beam, then you get an image of the object. This is how holography works. And here we have kind of a nice analogy to holography in the photoelectrons. Yeah. I should add that this technique has been used to probe, say atoms or molecules that undergo dynamics. However, the reconstruction process or procedures have not been developed so far that one could actually retrieve the molecular potential at which the electron scatters. Yeah, so this is there's still many open questions, and there are several issues with it that make things a lot more complicated than one would hope for. And one of the reasons is, of course, that the impacting wave, the wave that like the recolliding electron, is not a plane wave. So this wave is actually not very well known. And only then one could do this reconstruction. Okay, are there questions on the interference effects? Okay, so if this is not the case, we'll take a 3-minute break and then we continue with the molecules. Thank you.